member of SEG and a member of AGU. For today's session, Sir will be covering the topic of future research trends in AI, DS, and Earth science. Now, I will request Sir to continue with this today's session. Sir, I hand over to you.
Okay, thank you, Priyanka, for the introduction. So let me briefly share my PPT. So my PPT is visible to all of you, just to confirm.
Yes, it is visible, but kindly make it in a slideshow mode.
I have made it right.
Yeah, now it is okay.
Okay, so uh, as Priyanka mentioned that I'm working on interpretation of geophysical data. So here in IIT Bombay, what I do actually is that I try to develop the interpretation algorithm to interpret uh, one branch of geoscience or UN in earth science, geophysics. So there, how we can interpret those geophysical data sets. So I'll briefly introduce what we do. So, as an outline of my presentation, what is the motivation to do this kind of geological problem? How we can understand a typical geological problem? I'll go through with that. And basis of all the interpretation throughout this is one branch of geophysics. We call this as a geophysical inversion. So I'll briefly discuss these fundamental aspects, and then what is the problem we were facing currently to interpret using these inverse problems, and then how we try to overcome with this problem using uh, uh, AI and machine learning and deep learning to overcome these problems. So these are the some of the research development which we currently discusses, and then further I'll conclude this one. So if in general, if you talk about a geophysical method, so broadly it will be classified into seven. We call this as a seven step framework to understand any kind of a geophysical problem. So in the first setup is that uh, we see our Mother Earth as a geological unit. So if you wanted to get any kind of a resource, for example, oil, gas, uh, even mineral or groundwater. So if you wanted to exploit those research from our Mother Earth, then you have to be a very good knowledge of geology. So this is one of the aspect. Now, once you have a knowledge of this particular geological setup, what is important for us is that in which geological setup we are going to get some kind of a natural resource. You can consider anything. You can consider even oil and gas. You can consider minerals. You can consider even groundwater also. Okay, so important parameter will be that which are the physical property which is going to help me to differentiate between uh, uh, natural resources, rich rock, or which resources which is not having that particular property. So how we can differentiate which physical property is going to differentiate? If suppose as example, let us say that if mineral if magnetic data is going to have the differentiate these particular geological data, then what we do that we collect gravity magnetic data based on that. If there will be a DC resistivity data which is going to differentiate different geological unit, then we'll collect the DC data. Or so similar way, there are different branches of data sets which we collect. Once you collect that geophysical data set, it will look like if you process this and if you plot in a contour section, it will give you some kind of information where you are getting your anomalous area, uh, by which you can target. Now the main task is that this data you are measuring on the surface of the earth, right? But important thing is that these data, how you can obtain the subsurface image, uh, which is more valuable, and based on that how we can interpret. So in this particular step, from 4 to 5, our inversion comes into the picture, where from the data set we try to obtain a typical model. Usually we apply geophysical inversion. Geophysical inversion is nothing but, you can say that it is a kind of a numerical optimization problems. So I'll come here that what are the different problems, and then if you are getting certain subsurface image, from this subsurface image, again our task is that to interpret this subsurface image in terms of geology. And sorry, then after getting the geology of this area, then if you are getting some kind of a knowledge of this area, then you further transform this to whether this model is having a sufficient knowledge it is giving, and then you will go for your project completion, towards project completion. If you are lacking, then you will repeat the project similar way until unless you will complete the project. So this is the overall framework how geophysics works. But our research domain works on from step 4 to step 5, how quality image we can obtain from a data set is our more focus, which we try to discuss and try to develop here in IIT Bombay. Now, as we mentioned that our research interest is geophysical inversion, and main focus is on how we can develop and interpret different kind of geophysical data sets. So we collect these kind of geophysical data on the surface of the earth, and we try to model a different subsurface structure, what is on the below the subsurface. So in my expertise, if you ask, particularly belongs to this, we call forward modeling and inversion of that. There are different branches of data sets. I usually deal with electrical resistivity data, electromagnetics, some of the shallow components, some of the deep component, and gravity and magnetic data set as well. Uh, there are other methods like seismic and seismological data, which will usually deal for oil and gas and also for earthquake. So which I do not cover in our research. Now, one of the important component while following these modeling and inversion steps is that how you are going to discretize your subsurface earth. It is very important because there are many ways to look your mother earth and parameterize your model. So model parameterization meaning is that how you are going to represent your mother earth. For example, if you take image A, they have considered only three concepts. So whatever the node point you are seeing over here, they have considered this as a model parameter. And if you change this node point's location, then your model parameter will change. So we call this as a polygon based model parameter. This will help us to identify a very good quality object based optimization. If you wanted to do, then this kind of a model parameterization will help you. Second kind of model parameterization is will help you that to identify the layered structure. In that layered structure based model parameterization, what you do, you will take a control point like that, whatever white point you are seeing over here. These are my control point, and these control point, if I'll optimize through any kind of inverse problem, then these parameterization will control my layered and subsequent unit. You can easily see that, for example, here this blue color unit is not going further from here to here, so I have made it 0 0 0. So you can see that layered structure is not coming over there. So this kind of a parameterization, different authors have reported in a different field. What our research group does, usually we do discretize our mother earth in terms of meshes. Either you can mesh in terms of rectangular based meshes. Later I'll also discuss unstructured grid-based meshes. Why it is important to discretize your Mother Earth in unstructured grid-based? Yeah, here. So unstructured grid based will give you more flexibility to represent your Mother Earth. For example, here you will get two kinds of advantage. One advantage is that in this kind of a rectangular grid based, you can't represent irregular shapes because of the rectangle. You can't fit all the models. So if you wanted to have any kind of irregular structure, then best possible way to discretize your Mother Earth in terms of triangular. Of course, if you are working for a 3 dimension, then you should discretize your Earth in a tetrahedron. And another advantage of this unstructured grid-based discretization is that uh, one of the faces, you will see that uh, you can represent your topography in a very effective way. So one of the advantage is that topography can be also incorporated very clearly while dealing with the unstructured grid-based discretization. So these are some of the advantages of this one, why we go with that. And my one of the important point I would like to draw over here is that whatever the data which you collect over here, uh, whenever you try to optimize this one, so there are very clear cut framework by which you keep your data set. Though you are collecting this data set in a contour pattern meaning is that you are collecting the data in x direction, also in a y direction, and some of the physical property value. For example, here in this case, we are measuring in the field total magnetic uh, field. Okay, so if you are computing the total magnetic field, suppose this is your data set of total magnetic field, so you will keep, though you are collecting in a 2 dimension, but while doing the forward modeling and inversion, our terminology is very simple. We always keep our data set in a column mode. Okay, so all the 1500 data points, if you are collecting over a certain region, you keep in such a way that it should become a diagonal. And now, if you wanted to compute this kind of a model parameter, so your model parameter which you are going to optimize, it should also you will keep in a column mode. Now, our target is that from this data set, how we can compute this kind of a model, which I have represented with this cartoon. From this kind of a data set, how you are computing this kind of a model. So here you can, whatever the model I'm representing in this figure is actually M, and I'm keeping this in a column mode. Whatever you are seeing here data, it is D, and I'm keeping in a column. So this is just to how we are fixing these column mode and data mode of that one. Now, important part of this one is that how we can optimize this one. So one way of optimization is that many of you already aware that to compute the minima of a certain function. So this is the very similar way. So what you will do, you will proceed. One of the classical way is that Gauss-Newton based minimization, which is the many people also aware of that Gauss-Newton based minimization. Uh, Many of you also aware of that least square curve fitting, or some people also say linear regression. So these kind of a problem will be there. Whatever the data set I'm keeping over here is this representation, and this is my theoretical forward response which I'm going to fit into my model. And these are some of the model regularization term which will going to help me uh, how beautifully I can model my terminology. Now, important point I would like to draw over here is that since this is my minimization function, so there is the role of this P is very important. Sometimes what will happen in geophysics, that if you wanted to look very abrupt changes in your subsurface, for example, fault kind of feature, so then you have to choose a different kind of a norm. So L1 norm, suppose you want to see. So usually we use this kind of a norm to define that. And now if you wanted to see the smooth variation of the subsurface, then we use a L2 norm for that. So these are some of the different, you can say that architecture which you follow for that one. Now, the important part is that when you compute the differentiation of this particular equation with respect to M and equate to 0, you will get this kind of a update equation, uh, that is not so important for you. But what important parameter over here you should think that each iteration point we try to minimize this gap between measured data in the field and whatever the theoretical data we are computing. So we are trying to compute the minimum value of this one, and each time you, based on this minimum value, you will get delta m, and you update this one in the next iteration, so you will get your perfect fitting of that one. And this difference d obvious versus dk, or you d obvious versus d predicted, you compute in terms of root mean square. And this root mean square error usually we try to compute with respect to iteration. And if you follow the iteration of this one, this rms value of this particular data misfit, you will see that this is continuously decreasing, and you will reach certain point that it is no more it is not going to further update your model parameter. Then you'll close your iteration and you'll say that, okay, whatever the m value you will get, you just visualize it and you plot in a certain diagram such that you are getting the visualization. This is the classical way how your modeling and inversion part will work. Now, this one was the basis of the research. Whatever I have mentioned so far, this kind of inversion and all these things, this one was the basis. Now let us take this as a one example. I would also say that as a problem statement. What is my problem statement? That suppose we wanted to image this kind of mother earth, which location is varying from 0 to 750 meter, and depth is my 0 to 100 meter, which is a very near surface physical property. And let us say that this is our mineralized ore body, which is, you can see over a different color I have put. This is the sky blue and this one is the little reddish. uh, Now important point is that suppose I wanted to, this is the synthetic data, and I wanted to compute the inversion of this one, and the result was represented over here. Now physical property here I am trying to optimize is resistivity. So resistivity of this homogeneous sky blue color is 1 ohm meter, and resistivity value of this dye kind of a mineralized body I have taken 100 ohm meter, or even 500 ohm meter, or you can say 700 ohm meter. Now important point is that once you draw this 100 ohm meter body, you try to invert the value of this 100 ohm meter. What you'll get that if you invert this one, you will get this image. Now if you compare from the earlier image, you have recovered well, but only difficulty is that uh, it is actually the lower or higher side because of the inversion algorithm. I'll say that one. For example, this value I have taken over here as a 10 ohm meter, but here if you plot the histogram of this whole block, you will see that this value, some blocks are coming around 0.5 also, like that. So 10 to the power 0.5, because I have taken on the log scale. So it is 2 ohm meter, 3 ohm meter, it is also coming. And also same is go with the 100 ohm meter resistivity. You can say that it is also exceeding 200 meter. So point here I wanted to make that because of the consequence of the inversion algorithm, our model will not be, you will not obtain the exact model whatever you are looking. So how you are going to improve? Now another disadvantage of this one is that it will create the problem for that one. For example, here if I'll ask you that where is the boundary between these two geologic units, you are very certain that okay, in this direction boundary is here, in this direction boundaries is here, because up to here to here very drastic change is there. But if you look the inverted image, you can't guess that where is exact boundary. I can say that one physical property here to here, so that boundary can also be here. Someone can say that no, the boundary is belonging from red to little greenish one, so boundaries is belonging to here. So these kind of a boundary related problem will come when you will perform the traditional inversion. Now important basis of this talk is that how we are going to utilize the uh, advanced interpretation, uh, like machine learning or deep learning tools to improve these kind of images of that. Now important point is also that this is the optimization problem for this traditional inversion framework. Now, what kind of a optimization problem we should define such that we can get more and more improved result? So these are the things which is we should keep in our mind, and further advancement we should do. Now, one bracket is that machine learning algorithm. So we utilize two types of algorithm: machine learning based algorithm to improve our this imaging, and second is that deep learning based architecture we have also tried, and those results we are going to discuss and uh, but one thing I would like to highlight, that one, there are many branches of machine learning. Even I do not know, though I have a almost 5 year of post PhD experience in this earth sciences. So far now there are very limited uh, algorithm we have tried, but we have got some good you can say that good uh, qualitative image which is going to discuss. Now, important task is that how we are going to formulate our problem for that. So this equation, whatever you are seeing, exactly the same equation which I have written over here. I am more concise and I have put into the one equation. So that is why all are combined here. So that is why you are seeing in one top. So this is the traditional minimization function of any kind of a geophysical problem. Now, this is the mathematical basis of a machine learning based algorithm. Uh, Very precisely, we have used supervised based machine learning algorithm. So there are unsupervised based machine learning algorithm, there are supervised based machine learning. So specifically we have used fuzzy C-means clustering, which is the supervised based machine learning based algorithm. Now, important point is that what input value our machine learning algorithm will take from the inversion. So whatever the inversion you will do, you take this M as a further output parameter, you put over here for the machine learning, and you also provide some kind of additional output if you have anything, and you keep with you that, and then you obtain two more parameter. For example, here we are optimizing the fuzzy C means we are utilizing. So this is the typical if you take this particular equation from here to first expression up to this one, this is the typical fuzzy C means clustering. Additional parameter we have added over here, and then we minimize and we obtain from this MK, we obtain two parameter. One we call this as a membership value, which will provide us the lithology of that one, and second is the mean geologic unit of the value. And further we what we call this as we call this as a defuzzification. So we'll use defuzzification to further compute the updated model parameter. So as a output we'll get M also, and mu will be help us to get our more differentiation of the geologic unit. So these are the additional parameter which is we are providing to our model parameter to that. So whatever this algorithm we develop, and we also reported to the journal, and we name this algorithm fuzzy constraint inversion, or even we can say that fuzzy cooperative resistivity topography. So you can search on Google fuzzy constraint inversions. For more detail, you can get the rough idea. So basic idea over here is that this is the traditional inversion result, and this one is actually the machine learning based. So two different framework we are going to utilize to improve our model. How we can improve this one, and then we have further to see. Now, second, before showing the result of this machine learning based architecture, let me first show you that what we are going to deal with the deep learning approaches. So another important aspect was the deep learning based model architecture. So as all of you are aware that uh, training is one of the important parameter for to train your network, right? You consider any network, whether it is a segnet or whether it is unit or attention unit or variational encoder decoder network, any network you consider, one of the important part is that how you are going to train your model. So one of my PhD student we reported that a very important framework by which how we can effectively uh, effectively we can train our network in such that uh, many realistic model can be generated. For example, over here, suppose you wanted to draw this kind of a realistic model of this one. This is a very realistic model whenever you are going to study submarine groundwater uh, of that one. For example, this is the low resistivity is actually the uh, seawater resistivity value, and this one is the your main water aquifer, you can say, and how effectively you can integrate this one. So here to train, we have developed our own training module. What is important parameter here is that red node, whatever you are seeing on the red dot, is actually the control point. We are setting the control point, and each control point we are controlling the thickness of each layer. For example, here thickness of each layer we are keeping like that, so it is going like this one. So that based on this first layer will be automatically generated by the algorithm. Now the second layer is going from here to here up to this point, there is no layer, so you can see that this is just uh, ended over there. Third layer is going like this, so this is your third layer, and then in these layers you provide the resistivity value. Now you change the all the parameter. Even in the training model you can change this control point, you can change the thickness value of the layer, even you can change the thickness value of layer 2, you can change the thickness value of layer 3 as well as layer 4 as well. Now apart from that, you can change the resistivity meaning is that physical property of this one, and then you will get subsequent model of that. So this way we train millions of different architecture whether layered on that one. If you wanted to generate a 2D feature for this one, then you just keep these two 0 0, then here you will see one beautiful 2D feature of that. Now this way we have trained our network for deep learning. Now second more important aspect come for the deep learning approaches is that how you are going to train your network using which kind of architecture. So my student who is currently working on this unit architecture, attention unit architecture, and VED network. So what he is that he by following the previously published literature, he's trying to develop different architecture to train our model network, which is based on that one. Now important point I forgot to mention over that, this is the one subsurface image which is a true resistivity data. Now from this true resistivity data we have a clear cut physics belongs to generate the data set. So whatever the this model, you can generate the data, theoretical data you can easily generate based on the forward modeling of that. Okay, now these are the different architecture we worked on. For example, 2 to 4 square values we consider. So these are the different one. If you wanted to know the more detail of that, how he worked and he developed for that one, please you can feel free to discuss with us. Now second important aspect is that we also compare different architecture, because we at that point of time we do not know which architecture is going to provide a better subsurface image. So that we are trying the different architecture. We also train attention unit based architecture. We followed the literature of this Oktai et al 2018 for that. Now this one is the variational encoder decoder based architecture, which uh, presently this architecture was not for the geophysical application. So our student developed this architecture and we are trying to see the result of that one. So whatever this image you are seeing, we'll see the field data based image you will take over here, and this is the model we are getting that one. This model we can train and we can compute from this one based architecture. So this is why we are getting, and we have generated too much data set and we have trained our network to get different result of this one. Now with this our main objective is that uh, our main task over all these two aspects of this one is that how we can improve the mathematical basis of this expression. What is the important parameter which is going to why we can utilize those architecture and how we can improve our subsurface images. So one of the important aspect you should note that how we can improve the image and how we can separate the geology also. One of the thing I forgot to mention that uh, geology identification is also very difficult. You can try to recall from my earlier talk where I was discussing a 7-step framework. There I have discussed that uh, geology is the one of the important tasks from where how we can obtain your model. So now this one is something which is we are not computing from the geophysics point of view. For example, if you have any kind of a data set, from that data set if you are computing the resistivity value or density value, anything from that density, what will be the particular geologic model which you can compute. So we were not computing that one, and there were author who reported that how we can try that. So machine learning we utilized for this to identify. Only difference was that there were different people. I think it is Ward et al. 2014. He belongs to I think he is in BGS, British Geological Survey, and he used this machine learning based architecture, but as a simply post inversion step. Why I'm saying post inversion step? He obtained the geophysical model, and then after geophysical model he played with the machine learning and to obtain the final geologic model. Now here what we attempted that rather than optimizing in the post inversion framework, we tried to optimize within the inversion framework such that there should be no biasness towards interpretation. So this one or two important differentiation in the objective we made, and we try to play with the our algorithm. Now if you try to see the result part of that one, uh, I would say that the first example, let us take that. uh, any doubt on that? Someone was putting some question because my chat box is not visible. So any doubt, if you have, please raise your, you can directly communicate with me. If you do not have any doubt, then I can start.
Hello, sir.
Yeah, go ahead.
Am I audible, sir?
Yeah, you are audible. Go ahead.
Hello, sir.
You are audible. Please go ahead.
Sir, what is the importance of using a model regularization in a minimization of objective function?
This one you are talking. What is the role of this one?
Sir, at the start, yeah, you said about model regularization. So how it help in minimization?
Okay. One of the important objective is that we wanted to whatever the data you are computing in the field and whatever the theoretical model you wanted to theoretically your data you wanted to generate, our major task is that you wanted to fit that, right? One of the primary task is that. Now this model regularization term is actually deal with the what kind of a model you are looking in the subsurface. Many a times we encounter that uh, these model parameter will not be like that. For example, fault kind of a subsurface. Suppose within the subsurface we wanted to model a faulted kind of a structure. Now geophysically, what is the meaning of fault? Fault meaning is that you are going in a certain direction and there will be sudden disrupt of the change in the lithology, and you suddenly sharp changes you will notice. So if you wanted to model a sharp change in the model, you will use the help, you will take the help of this model parameterization. For example, I'll choose p is equal to 1. P meaning is that here I wanted to compute norm, LP norm, L1 norm, L2 norm. So I'll change my norm parameter, and apart from that, this parameter whatever you are seeing, this wi and ws, actually it is a gradient of this m. So x direction gradient, z direction gradient, if you are in 3 dimension, then y direction gradient also you are computing. So which kind of a gradient you are computing? So these are the some of the combination of all the parameter which we are going to help. If you do not want to model faulted like structure, then what you need to change your model parameter to p is equal to 2. P is equal to 2 meaning is that you are going to perform the minimization with L2 norm based inversion. What is the meaning of L2 norm? L2 norm is usually used for a smooth variation in the subsurface. So in the subsurface, you are going to see smooth changes in the subsurface. For example, groundwater, if you wanted to look for the groundwater recharge or this kind of a, you will see that resistivity variation will be smoothly decreasing in this kind of a geological scenario. So what kind of a subsurface you are going to look, based on that you will choose your model regularization for that. Hope I'm clear.
Thank you, sir.
Yeah. Now, let me come with that this one with how we can how we have implemented these two. I mean, one was the result of deep learning, one was the result of machine learning, right? So let us, I'm showing the one by one the result of, first I'll show the machine learning one. Let me show you how we have tried to improve this one. So let us have one case study. So this is the actually the DC resistivity data. I will just briefly introduce the what is the meaning of DC resistivity data. In DC resistivity data, what we do, we try to inject electric current into the subsurface. Suppose you are injecting I amount of current into the ground, and you are measuring the potential value, potential difference between the two electrode. So you will need a setup of 4 electrode. Two will be the will work as a current electrode, another 2 electrode will work as a potential electrode, and you will compute the, you will inject the current I into the subsurface and you will measure the potential V. And based on the Ohm's law, you can easily compute the resistance of this one, resistance. Now based on the resistance value, uh, and based on the location from where you are injecting the current and where you are measuring your potential, you can easily compute one of the parameter. We call the parameter as a geometric factor. This geometric factor further multiplied with this resistance will give rise you the apparent resistivity. So we measure apparent resistivity value of the subsurface. How apparent resistivity will look? This kind of a typical apparent resistivity look like in image A. For example, we laid our electrode on 0 meter to 700 meter, and then we measure the different combination of the current electrode and potential. So we got the apparent resistivity value. I plotted in the log scale. 0.5 meaning is the 10 to the power 0.5, actually it come around 2 or 3 ohm meter. 2.5 is meaning is that it will come around 500 700 ohm meter. 10 to the power 2 meaning, with yellowish color meaning is that it is, you are getting 100 ohm meter. So this one is the field data you will collect in the field. Now from this field data, how we can utilize the traditional inversion, how we can utilize the traditional inversion plus machine learning, how we are going to improve the image, I'll show it over here. So the study area was for the landslide study. One of the important parameter is that the DC resistivity profile was laid out like this, and B1 B2 whatever you are seeing over here is actually your B1 B2 is actually your bore well which we drilled over the region. Now this one was the study area belonged for the natural hazard study, to be more precise for the landslide study. Now already aware of that one, landslide is how important the parameter uh, to deal with that. Many a time you will see here in the newspaper that uh, in the Uttarakhand region, this road was blocked because of the landslide. Many things will happen in mainly on the rainy season. So the mitigation of this one is become the important parameter. Now, what we do that from the data, this is the data which we have collected, and if you perform your traditional inversion, which I discussed mathematical notation of that one. So there are two main thing we compare. Here we develop our own architecture for the interpretation of the resistivity image. Here is the resistivity RES2D and the one of the software to interpret DC resistivity data. I think each I think institution must have this interpretation software. So now you can get the idea that okay, this is the clay feature you are getting over here, which is the responsible for a landslide which was sliding over this clay was sliding over this one. So this one was the responsible for this one. So that is why this landslide was occurring. So you have to mitigate using this one. Now, important parameter for this one is that how additional parameter we can get that. So additional parameter, what we get to utilize our machine learning based algorithm was this borewell. Borewell 1 is located over here. Borewell 2 was located over here. And what is this borewell? These are the resistivity value of this borewell. So resistivity value of this log is varying. In these two, it's varying like this. Now, important parameter is that this depth, if you will see the value of this depth is only 25 meter, which is I think up to this one only. And B2 is also very similar, I think 20 meters. So it is very near feature, but we wanted to model 60 meter. So we transform this resistivity value of this well log data into some kind of a parametric domain value. What is the meaning of parametric? Parametric meaning is that we, irrespective of depth information, we just sample this value and plot in the histogram, and we got that okay, what are the histogram plot of these values. So we got some good quality peak of the value. One we got this 100, one we got from this peak, one we got over here, and another was which was not belonging to this region because borewell was only located, if you see more precisely, borewell was located over here and B2 was located along this one. B2 parallel to this one, so not exactly on the line. B2 over here, B1 is belonging little slightly there, but if you draw the line, it will belong to this location. Now we utilize these two another framework. We put these two information in this equation. To be more precise, let me draw here. We utilize this expression. We put the value of this cluster value and we obtain further these values. So these help us further to compute the more model set. Now let us say that if by utilizing these feature, what was the result we got? Let me show it to you. This is the result we got after the combination of traditional inversion with the machine learning. Okay, to be more precise, supervised machine learning based. So now you can see that the boundaries were not that much clear between these two geologic units. For example, dry crust clay and unleached clay, you can't differentiate. Similar way, you can't differentiate bedrock versus unleached clay. Boundary, where you will draw the boundary, here you will draw or here you will draw. So these things were little confusing in the present model. But if you see over here that the boundaries is very clear, bedrock over here, dry crust clay is that one, leach clay and dry crust clay is like that. So similar way you can differentiate these two. So boundaries got very precise, and we were able to see much more variation of this one. Now as a practice, we always compute this model parameter for this one. So we computed this value over this model to the fitting one, and then we further computed further more model to fit that one. So this one was the computed model for the only using the Gauss-Newton based inversion, without any machine learning tool. This one was the fitting of the data using deep machine learning plus traditional inversion. You will notice that there were good quality fitting as well, because here you will see that some of the feature are here, it is also fitting that one. But if you notice over here, there is, but all are fitting in a very good quality. Also, if you see that this image, you will see this is just a simple the difference between these two. So you'll see that still some pattern is showing over here. But if you see comparison of these two difference, you plot, you will see that the random pattern you are getting, or more likely here you are seeing little bit vertical pattern. So these are some of the fitting comparison. So point I would like to say that we are improving our subsurface quality image but at the same time we are trying to honor the fitting as very similar to what we are computing in the traditional inversion. So these are some of the advanced image we obtain while we utilized our supervised machine learning based inversion approaches. So this really help us to obtain more quality images for that. So I think for the session one, I have done that one. We can take the break for that, and then further I can start from scratch. If you have any
Thank
doubt,
you,
please
sir,
let me
for
know.
thank you, sir, for your informative session.
Okay. Yeah, I'll take.
Participant Participants, we will be having a 10 minutes break and will continue from 8 p.m.